Okay, so last time we talked about some of the mistakes that science can make, whether by subtly introducing bias into the scientific process or by trying to push science into non-scientific domains. And check that video out if you haven't seen it yet. But science isn't just vulnerable to error from the inside. From the outside too, science can also be misunderstood or misapplied. It's easy to invoke science as a stamp of credibility, even when we don't fully understand its lessons or principles. And when we do this, we can draw conclusions that sound scientific but really aren't. Here's a list of 10 mistakes that non-scientists can get wrong about science. Number 1, underestimating the extent of modern scientific knowledge or misunderstanding scientific terminology and concepts. For example, believing that vaccines are unreliable or experimental or dangerous despite decades and decades of well-established science and large-scale trials. Or using terms like energy or vibration or quantum mechanics from physics, which can often become twisted into New Age spirituality and lose their original meaning. Or assuming that, for example, because microwave ovens and cell phones emit radiation, and radiation causes cancer, that therefore these devices cause cancer, but failing to recognize that the radiation emitted by phones and microwaves is non-ionizing, and even sunlight is more likely to cause cancer than these devices. Failing to understand scientific concepts while simultaneously invoking them can lead people to make overconfident or pseudoscientific claims, or conversely to assume that science is unreliable. Number 2, confusing correlation with causation. For example, that children shouldn't sit too close to the TV because it will cause myopia or nearsightedness. But in fact, it's myopia that causes children to sit too close to the TV. Or, for example, assuming that consumption of ice cream causes increased risk of drowning, when in fact it's a third variable, hot weather, that causes both increased ice cream consumption and increased swimming, which leads to increased drowning. Number 3, expectations of absolute certainty from science. Now, science cannot predict any outcome with 100% certainty. There will always be some probabilistic element or based on our current scientific knowledge disclaimer. This can result in the non-scientist rejecting sound scientific claims when they are not made to seem absolute or black and white. Instead of understanding science as nuanced or self-correcting, it can be seen as unreliable or contradictory. Number 4, cherry-picking evidence without methodological rigor. Now, good science should exhaustively try to prove its hypothesis false, and only if failing to do so, suggest that it may be true. Instead, non-scientists may select studies which confirm their hypotheses while intentionally ignoring studies that refute it. Or even within a single study, people may select claims or evidence that support their ideas while ignoring other parts of the same study that refute them. This can look like the use of science as a tool for the confirmation of an ideology rather than unbiased exploration. Number 5, misplacing the burden of proof. This can be expecting science to disprove any given claim rather than providing scientific support and evidence of an opposing claim. For example, if I were to say, you can't prove that unicorns don't exist. But in science, we typically treat any claim as if it's false until proven, or more accurately suggested, by evidence to be true, not the other way around. Number 6, equating simplicity or rationality with scientific truth. Now, just because something is rational or logical or poetically balanced or synchronous within some larger ideology or framework, that doesn't mean it's true. All science is foundationally based on empirical observations made through controlled study, even when the results are undesirable or unfair or nonsensical. Number 7, assuming that all ideas deserve equal scientific weight. For example, giving ideas without scientific evidence or justification equal weight to those with robust evidence and a plausible mechanism of action. For example, the Earth is flat versus the Earth is round. Climate change exists versus climate change is a hoax. There is or is not a link between vaccines and autism. In each of these cases, one side has far more scientific support than the other. Number 8, conflating mechanism of action with impact of effect. Now, non-scientists may confound mechanism of action with impact of effect. In other words, assuming that a known mechanism implies a predicted effect, without evidence that this is actually true. Because even if the mechanism exists, the actual effect may be negligible or can be balanced out or even outweighed by other competing mechanisms. For example, a food may contain pesticide residues, but the concentrations may be far too low to be biologically impactful. Or, for example, we know that caffeine is a diuretic, that it causes increased urine output. This is true, but the water loss is much smaller than the water gained, for example, by drinking a cup of coffee. So the net effect is hydration rather than dehydration. Mechanism doesn't always imply effect. Number 9, assuming that incomplete scientific knowledge is equivalent to support for alternative, non-scientific conclusions. For example, when COVID-19 vaccination effectiveness was uncertain, other alternative treatments, like horse dewormer, may have been interpreted by some as more effective, when in fact, again, those treatments were not supported by any evidence. When scientific evidence in an area is lacking, it doesn't mean that alternative explanations, which may have even less scientific support, are necessarily more likely to be true. And number 10, believing that anecdotes are equivalent to data. Now, anecdotes and personal experience are useful for creating hypotheses, but they are no substitute for rigorous experimentation. Stories may be compelling, but they fail to capture the objectivity and randomization of controlled studies. And that's it. These are some of the pitfalls that we can fall into when interpreting scientific data and concepts outside of our expertise. Thanks for listening.